and then it's my pleasure to introduce the first of our speakers. I was trying to think of the most embarrassing story I could think of about Arno Villringer. Fortunately for him, it's been 25 years, and so most of them have been forgotten. But I don't know that we all really appreciate just how fortunate we are, and just how some little serendipity of science can impact on our career. Arno, of course, as many of you know, is the director of the Max Planck Institute for Human Cognition and Brain Science, is the academic director of the Mind and Brain Institute in Berlin, a very, very famous neuroscientist. Those of you, for example, working in the domain of optical imaging should know that the reason we're doing optical imaging at the Martino Center is because of Arno. He invited me to a meeting he was putting on optical imaging when I knew almost nothing about it, and I learned that it was pretty cool and we should be doing it too. We have him to thank for that. But I think we have something more fundamental to thank for him, and that's really getting this whole ball rolling. When Arno was originally to come here, after he graduated summa cum laude from med school, we invited him here actually to work on another project that we had going on the lab, lactate chemical shift imaging. We were actually the first to do proton chemical shift imaging, the first to figure out how to do water suppression and look for the subtle metabolites. We had taken some very crude pictures, figured what better than to have a neurology-oriented scientist come and work on that. But I remember it was Tom, I think, that told him that he better hurry up and get here because, if he didn't get here in the next month or two, the project would be complete. Of course, we're still struggling to do chemical shift imaging of, low concentration proton moieties. And that turned out to be a pretty challenging project. So kind of in his spare time, he picked up on the work that had come out of another group in the lab. I'll make some brief comments about that. And to start working on this concept of dynamic susceptibility contrast. So maybe had we made a little more progress on lactate imaging, you would have stayed with that and never would have picked up the susceptibility mantle, which of course, as you'll learn, turned into something quite important. Fortunately, that was a really hard problem, so we only gave you kind of a hard problem, and that's to figure out how the brain works with functional imaging. So with that, Arno, please come up and share your thoughts with us.
Thank you very much, Bruce, for the kind introduction, for the invitation. It's a great honor for me to be here. Welcome. And the task is to report a bit about very early experiments. And early, in my case, means actually more than 25 years. It means 1985. And looking around, many of you weren't around in 1985. It was the time when this guy was just re-elected for president of the United States. These two people were quite important in the world. And actually, I came from a country, West Germany, which doesn't really exist anymore. So, yes, it was a different time. How was MRI at the time? I came here to learn about MRI, a technology just on the verge of becoming a clinical technology because I was going to become a neurologist. These were the kind of images that were published at the time from your center. This was imaging of a stroke, and it's the most important neurological disorder. So I was enthusiastic about learning about this and about doing lactate imaging in stroke. When I came here, actually, and I talked to people that I want to do something new, actually, people were quite skeptical. I mean, they said, no, you are too late for something new. That's not, don't invent this. This is really true. All major things in MRI have been done, such as T1, T2-weighted, 3D MRI. Yes, maybe there is some progress in spectroscopy, actually supposed to be done already, maybe in the field of contrast agent. So I started with those two projects and using MRI contrast agents, and the guy who developed contrast agents at the time at the MGH was Randy Laufer. The bad thing is he developed contrast agents for the liver. And actually, they only worked in the liver. They worked nicely. So this is a T1 contrast agent that we published at the time. But the brain was difficult because the brain has a blood-brain barrier and very little blood volume. And so all these agents did not work in the brain. Actually, then somebody in one of those liver experiments used, just by chance, a wrong pulse sequence, a T2-weighted pulse sequence. And lo and behold, the effect was even bigger than with a T1-weighted pulse sequence. And then the idea was, okay, if there is such a big effect in the liver, maybe let's try in the brain again. What about the brain? And this actually, I looked back in the copies of the notebook of the time, and this is, actually it was quite early, I came in January, so in March, I did this experiment. I injected the largest dose that was, I think all gadolinium that was at the MGH, into this poor rat. And yes, there was this effect. You see that there was a drop in the signal intensity in this T2-weighted image of the rat brain, which slowly recovered. So why was this interesting? Yes, it was interesting because it may be approached to measure cerebral blood flow. It was like other techniques that injected something in order to measure blood flow. Let's go back to the history, a bit of history on cerebral blood flow as a window to assess brain function. The concept has been introduced quite some time ago. Roy and Sherrington, more than 100 years ago, suggested that blood flow is coupled to brain activity, neurovascular coupling. And of course, it was always a window to measure cerebral blood flow to look into acute ischemic stroke. So this was kind of the first ever experiment, invasive experiment, using this idea of neurovascular coupling for doing functional imaging in humans. This was a poor guy called Bertino in the 19th century who had this wound to the, you don't see this, I guess, this wound to, after some kind of accident. And so he had a hole in the skull. And his neurologist, Mosso, actually, he was interested in measuring the pressure through this with a so-called sphygmometer. And actually what he noted is that when Bertino was calculating or did some task, this pressure actually increased. And actually now it has been detected recently that he did a large body of such studies, basically taking advantage of neurovascular coupling very, very early. But it took some time. In the 20th century, people developed agents, radioactive agents, that they could inject. And I think the pioneers were the group in Denmark by Lassen, Ingvar. They used xenon, injected it in the brain. Actually, they injected it, as you can see, as a bolus into the carotid artery. Quite invasive at the time. And then the images were quite astounding. So a 1 cubic centimeter resolution of functional imaging. And then PET arrived, improving spatial resolution. But still, of course, you were dependent on the injection of a contrast agent. And of course, I was interested in neurology. PET was also used in clinical imaging. So based on blood flow, you could also diagnose a stroke and follow up reperfusion. So in summary, the first very invasive measurements were done in the 19th century. The first measurement of global blood flow by Kitty in 1944. The first regional CPF measurements by Lassen and Ingvar, and with radioactive xenon. And then in the 80s, positron emission tomography came around. But of course, the drawback of all these approaches, they used radioactive contrast agents, they had poor spatial resolutions, and also only a few time points could be done, so there's no continuous measurement of brain activity. So now back to this finding, which actually turned out to be quite difficult to reproduce. I don't know, because when I tried smaller doses, I couldn't reproduce the finding. And then if you look, this is from my notebook, if you look at the temporal resolution, it took 2 minutes, almost 2 minutes, to make such an image. And actually, I had to go into the room to inject the contrast agent and come back, and the first pass effect, of course, had disappeared already at the time. So that was probably the main reason why we couldn't reproduce the finding in the beginning. So it was important to have a faster temporal resolution. At the time, however, there was no fast imaging. There was no echoplanar. There was no other types of fast imaging. So I tried to develop a pulse sequence which basically took temporal resolution instead of spatial resolution by relying on a single line. But of course, if you scan a single line, then you have basically an image across a cross section. You have more signal than just the brain. So I developed a double slice selective pulse sequence so that this hub only represented the brain. And then all of a sudden, we had a temporal resolution between 1 and 8 seconds. And then all of a sudden, when we now injected a contrast agent, you see this drop, and this was each a line of the brain, and you could follow the time course over the next seconds. And now we could identify this first pass effect. Now, what is the reason for this effect? T1 effect, T2 effect, what actually happened here? And the two main theories that we discussed was that it could be an intravascular magnetic susceptibility effect versus some strange still change in relaxivity via dipole-dipole interaction, which was the main effect known at the time. So how could we differentiate the two? So fortunately, there are, besides gadolinium GdDTPA, there are other agents which have the same effect on magnetic susceptibility, but different relaxivity. And so we used them in analogous studies, and now you see the substance dysprosium GdDTPA with the highest effect on susceptibility had also the strongest effect on our signal, whereas it basically followed the amount of susceptibility. So the highest effect of the agent with the highest susceptibility, and in the end, there was a good correlation between the magnetic moment, which determines the change in magnetic susceptibility, and the signal change that we observed. And so this was like the model that we put forward. Basically, the signal decrease came about by a change in intravascular magnetic field, surrounded then by magnetic field gradients, and they kind of destroyed the T2 or T2 star weighted image. Now, if this is true, then we thought, okay, that must mean that the line width of the water signal must actually enlarge. And then I came back to the chemical shift imaging that Bruce had developed, and we used this before and after contrast agent application, and I think you have to believe it to me, there's a very narrow line here, and after there was this broadening of a line, and I think this has finally proven that it's really due to a magnetic susceptibility effect. And then came Jack, and I had to leave the country. I went back to Germany, and Jack basically started his PhD project under supervision of Bruce, and yes, he said in 1885, yes, the goal of my PhD project is to make the visual cortex lightening up with this, which happened then 6 years later. Now, while you guys were inventing fMRI, I had the small problem that after having learned MRI in the United States, I came back to Germany, started a residency in neurology, and the radiologist who just got a new MRI scanner said, no, neurologists don't do MRI research. So I thought, okay, let's do something else which explains what I've been doing and what you have been developing in Boston. Let's work on the physiology of neurovascular coupling. Let's work with optical methods. And for example, actually the last experiment I had done together with Jack, we had the rats breathe hypercapnia. We induced hypercapnia, sorry. And the effect was much, much bigger. And so I thought, wow, that's amazing. We have proven something. We have proven that capillaries open and close, as the capillary recruitment hypothesis suggests. And of course, whether they open and close is very important for the modeling of the entire intravascular susceptibility effect. And so at the time, we developed a method to look at the capillaries directly, invasively, sorry, in the rats, but in vivo with confocal microscopy. We were the first to do this. And actually, we could go down up to a depth of 150 micrometer below the brain surface in vivo. And then we looked whether capillaries open and closed, for example, during hypercapnia. And actually, what we found, they never opened and closed. They were always perfused. And what we also could see, each line is a erythrocyte. When we induced hypercapnia, the velocity was the main thing that changed. And also we noted, which was also not known at the time, a slight increase in capillary size. And these were data which then again could be used for modeling of the susceptibility effect. Then we did something which we thought was quite cool. Until I talked to Bruce, so we measured with laser Doppler flowmetry continuously blood flow in the rat brain, again, invasively. So I remember, it must have been in the end of 91, I called Bruce and told him, you know, we do incredible studies. We can now continuously measure blood flow. We can identify the effect of NO and anesthesia and so on. And Bruce said, oh, that's interesting. But we are actually doing this now in humans, non-invasively. So I was a bit frustrated, to be honest. But of course, and of course, this guy, who looks the very same, Ken Kwong, had arrived and had developed a non-invasive monitoring of blood flow, or in this case, BOLD. Okay, again, we said, okay, so they invent fMRI, non-invasive BOLD. We just work on understanding the basis of this. So in our rat model, we could confirm that, which actually, I remember a phone call with Ken, and he said, strange enough, this signal goes up, shouldn't it go down? And yes, deoxyhemoglobin goes down, and we could confirm this in the animal. Actually, there was no dip, which is now very clear. We also could then, via near-infrared spectroscopy, show that on those places where there is a BOLD signal in humans, there is also a drop in deoxyhemoglobin, and actually during a deactivation, there's a rise in deoxyhemoglobin. And then, finally, as I said, I'm a clinical neurologist, so perfusion imaging was also invented based on the technique. And so in this case, we thought, let's try to follow the example of you. And the example being, okay, don't use an external contrast agent, but just take an internal contrast agent. And so we thought maybe there's also an internal bolus in the brain. Aren't there like heartbeat, breathing, which could serve as an internal bolus for the BOLD signal? And yes, and if that's the case, then there should, if there is something like an endogenous bolus, at least virtually, there should be a relative BOLD delay when perfusion drops, for example, in a stroke. And so by a simple cross correlation of the total signal, global signal, and a signal in each voxel, we were able, okay. Your device is ready to use? Okay. We were able to show, basically just on a BOLD delay, the same kind of perfusion drop in human subjects. And actually now we're doing this routinely, can even follow reperfusion after recanalization. Could I just? Okay. So now I, of course, went ahead in time just to tell you a little bit what I did since. But now let's go back to 1985. Let's go back to this strange finding, which did not look at all spectacular. When I came home to Germany and told them this was my major finding, people were a bit, okay. And I think I should now hand over to Bruce, who tells you how you guys did out of this, this. And before I end, I have to say thank you to all of you guys at the MGH Martino Center. First of all, for showing me that it's never too late. And then I should mention all these people: Jack Bellevue, Tom Brady, Ken Kwong, Van Vedeen, Randy Laufer, Alice Vincent, Rick Buxton, Jerome Ackerman, Bob Edelman, Bob Weisskopf, Jason Coucher, Brigitte Poncelet, David Kennedy, Bob Savoy, Mark Cohen, Larry Wald, and especially Bruce Rosen. I always felt like part of a family. It was always an honor and a pleasure to be kind of an external member of the group. Thank you very much for all this. Thank you very much for your attention.